All right, good afternoon, everyone. My name is Kevin Wagner. I'm the director of the Oklahoma Water Resources Center and want to welcome you to our water seminar today. Today we have Dr. Prem Bikkina with us. He's an associate professor in chemical engineering and is the Harold Corson Chair in Petroleum Engineering and the Petroleum Program Coordinator. So Dr. Bikkina and I have worked together for several years on produced water. Are there ways that we can treat it and make it more usable, not only in the oil field, but for other uses as well. And Dr. Bikkina is probably going to say this whenever he talks, but people are always amazed when I tell them, like, the average oil well in the United States produces 8 barrels of water per barrel of oil. So a lot of the research has been on other beneficial ways we can use that water that's produced during oil production. So it's not frack water, although that can be part of it. It's really broader than that, and like every oil well is producing this water. So he's doing some fantastic work that he's going to be talking about today. And he's going to be talking a little bit about some work they're doing related to the NSF EPSCoR program with the measurement of CO2 solubility in brines and hydrocarbons. For CCS, you're going to have to tell me what CCS is.
Yeah, carbon capture and sequestration.
There we are, carbon capture and sequestration and enhanced oil recovery. I know what EOR is. So Dr. Bikkina, I'll turn it over to you. Thanks for being here.
Thank you so much, Dr. Kevin Wagner. Good afternoon, everyone. So I hope you guys are hearing, like the online people. So as Dr. Wagner mentioned, the talk is on measurement of CO2 solubility in brines and hydrocarbons. For I mentioned only 2 applications here, CCS and EOR applications, but the EOR inherently has produced water disposal also, All right, so here is a brief outline of the talk. And since the talk is related to carbon sequestration, enhanced oil recovery, and produced water disposal, I'm going to briefly talk about them, for the people who are not probably aware of one or more of them. And then mention the objectives of this study and the methodology that we follow. And then I'll discuss the results and conclude it with some key findings that we found. So first, let us actually see what is CO2 sequestration. So obviously, we all know that the CO2 is a major greenhouse gas, right? And not because it is very potent compared to other greenhouse gases, but because of its potency, not potency, sheer volume. Compared to the other greenhouse gases, carbon dioxide actually is huge in terms of its volume. Overall effect, and hence is, it's a dominating effect. So 3 days ago, the atmospheric CO2 concentrations, it's a global average, is 421 ppm. That was 280 ppm, in 1780s, pre-industrial period, 150+% rise. So this is all man-made, due to the man-made activities. We know the consequences, on the environment, and so on. Don't need to mention them. So the sequestration, CO2 sequestration, is basically a technology that has potency to mitigate these adverse effects of global warming. So how it is done? Basically, they capture the carbon dioxide at the source, maybe a thermal power plant or other sources like refineries, where they can actually get a lot of CO2 emissions. And then if there is any purification required, they do it, and then they compress the carbon dioxide from gaseous to liquid or supercritical state, and then inject the carbon dioxide into subsurface formations. As this schematic shows here, typically the subsurface formations can be depleted oil and gas reservoirs, so or CO2 can be used for enhanced oil recovery, again in depleted oil and gas reservoirs. And then we can also inject CO2 into regular saline aquifers, so that is purely for storage purpose. But for other two applications could be, storage and also for enhanced oil recovery purpose. The fourth host site can be a coal bed seams. Like if we can actually inject carbon dioxide into coal beds, and due to preferential adsorption of carbon dioxide on the coal surface over the methane gas. So when we inject carbon dioxide actually goes and adsorbs on the coal surface and dissolves methane, like it is enhanced methane production. So we are actually solving two things here. One is we are getting rid of carbon dioxide and also producing oil and or gas, at the same time. So once the carbon dioxide is injected into the subsurface surface formations, there are like four major trapping mechanisms. Basically, if we inject carbon dioxide for sequestration purpose, the objective is, it should never go back to the atmosphere. It should be there forever. So what makes the injected carbon dioxide stays there forever is basically these four major trapping mechanisms. The first trapping mechanism, which is very important at the early years of the injection process, even during the injection, is the structural and stratigraphic trapping. In general, these host sites, are porous and permeable rock formations, but usually they are accompanied with a cap rock, low permeability rock on top of that high permeability reservoir. So that cap rock acts as a seal and make sure that the injected CO2 actually stays there. So that is structural and stratigraphic trapping. So then once the injection process is over, usually carbon dioxide is in non-wetting phase to typical these host sites. And once the injection is over, during the injection, the CO2 may be displacing the native fluids already in the reservoir, which are typically water and hydrocarbons. But after or maybe even during the injection itself, because CO2 is a non-wetting phase, the wetting fluids might actually come back. During that coming back process into the reservoir, some of that CO2 will be trapped permanently as a residual CO2 due to capillary forces, which is a very permanent, very strong trapping mechanism. And then, of course, CO2 can dissolve in the water or brine present in the reservoir and also in the hydrocarbons. That we call it as solubility trapping. Once it dissolves, and if those fluids are there, along with them, like CO2 is also there. And then finally, in the long run, mineral trapping, like the injected CO2 reacts with the fluids and the solids present in the reservoir and then form minerals, carbonate minerals. They are the most stable form of sequestration, but it takes really long time, more than 1,000 years, or like tens of thousands of years. So earlier years, I think structural, residual, and solubility trapping are important. And this talk is about, of course, all three of them, but mostly solubility trapping, because it is measurement of CO2 solubility in the aqueous and organic fluids. But that solubility will actually in turn affect the residual trapping and also structural trapping, and in the long run, even mineral trapping. So, so coming to the enhanced oil recovery part, I presumed at least maybe there may be some non-petroleum background audience here, and then I'm just briefly going to talk about what is a typical petroleum production system and how we produce the oil, the stages of oil recovery. So this is a schematic of a typical petroleum production system. What you're seeing it here is some major components in the production system. The number one component is obviously the oil and gas reservoir, without which obviously the petroleum production system would not have any meaning, because with no reservoir, other components have no purpose. And then obviously that's where we have oil and gas. And the reservoir, if we are talking about saline aquifer, it may not be oil and gas, but can just be water. So, and then we have a well, penetrated into the subsurface and of course, obviously to the reservoir zone. A part of the well, and that part of the well, we call it as well bore. And we have wellhead. If you go to any oil field, what you actually see there in oil well is this part, obviously, because the majority of the well is actually down below the subsurface. So then, of course, as we can guess, we almost always have oil under gas and water also in the reservoir. It does not necessarily be a saline aquifer. Even in the typical oil and gas reservoirs, water is always present because before oil and gas actually migrates to that reservoir, it was all water. So, and hence, some of that water will always stay there. And that water is what we produce, along with the oil and gas. And and hence, that's a very dirty water. We call it as produced water and very high saline. Sometimes we have, as nasty as like radioactive elements and all, organic waste and all those things, not useful for drinking purpose for sure. And even for agricultural uses also may not be useful as it is unless we actually treat it. And hence we cannot sell it to anybody. It's a cost to the company, and we have to, separate that unwanted water from the wanted oil and gas, and that happens right at the wellhead. And then the gas and the oil, goes on their respective pathways to either the end user or maybe refineries. And if you zoom it into the reservoir part, as I said, this is reservoir, a porous and permeable rock. This part, both the red, green, and the blue part. And the top portion is the cap rock or the seal rock. This is what is going to be actually holding the reservoir fluids in place. When we inject carbon dioxide into this reservoir formation, and this is what is actually causing the structural and stratigraphic trapping. It's like a seal of the box. So even within the oil zone, gas, oil, and water are segregated because based on their densities. Obviously, gas is the lightest, water is the densest. So usually we actually drill well into the oil column because it is easy to produce gas because it is lighter, lower viscosity, right? Oil is the most important thing. So even in the oil zone, we cannot assume that, it is 100% oil, there would be water as like this is a core sample from that zone. And then when you zoom it into that porous rock, at a pore scale, you can see those blue rings, they are actually water. We have water even in the oil column. Okay, so obviously reservoir is a porous and permeable rock filled with maybe partially or like fully hydrocarbons, right? So it is down below the surface of the earth. As we can rightly guess, as we go down deep into the subsurface, the pressure and temperature rises, right? Drilling a well into that pressurized environment is like putting a hole to your soda can or something. What happens? It is under pressure, right? Once you drill a well and complete it, that natural pressure energy lets some of that initial oil and gas to produce on its own. That's the best phase of oil recovery because we are not actually using any external energy source to bring the fluids from the subsurface to the surface. And then obviously pressure is a finite source of energy, and it would quickly deplete, depending upon how we are operating. And then by the time that pressure is depleted to such a level where it is no longer useful to bring the fluids to the surface, we would, in the worst case, probably we would only produce 5% of the initial oil in place. So still we have 95% left there. And so then we know the reason why the remaining 95% is still there. It is pressure depletion. So obviously, since we know the physics, what is happening, anybody would actually attack that right parameter in order to, get maybe some more oil out. That is actually secondary recovery, where we inject a cheaper, environmentally okay fluid to repressurize the reservoir, through injection wells. And we inject, let's say, water, not very potable water, maybe seawater, or, or water produced from the same well or same reservoir. And then it repressurizes the reservoir and then sweeps some of the remaining oil towards the production well. And it causes some more oil recovery. With that, we may get additional 10 to 20% of oil. So in the worst case, lower end, if you add like 5% and 10%, 85, still we have 85% even after the secondary recovery. At this time, what is happening is at the end of the secondary recovery, for example, if we are injecting water, as a driving fluid or displacing fluid, so we are injecting water and we are producing water. That would not make any sense because, we are not getting any oil out. We have to, stop and see like, what else we can do to get oil, more oil. So obviously this time it is not the pressure depletion because we can inject as much water, right? It should be something else. And we will discuss quickly what is that something else. And then we need to attack those things to get any more oil. That part of the recovery, we call it as tertiary recovery or enhanced oil recovery. Okay, so again, let's first discuss, what are the reasons why the secondary recovery is failing after some time, and so that we can attack on those reasons. There are some 4-scale reasons. You see this schematic here. The yellow grains represents grains of the porous matrix. Like if you have a rock has grains and pores, right? The yellow is grains, and in the pore space, the red is oil, and you have the blue rings surrounding to the sand grains that represent water. Already existing in the reservoir. Of course, it is a 2-dimensional diagram, and hence the water looks like it is not touching from grain to grain, right? It looks like a discontinuous phase, but actually water is the wetting phase. Grains are touching each other in 3D, and it is a continuous phase, always, no matter what. Oil in this schematic is continuous. First one, continuous in the sense like you can go from one side of the reservoir to the other side of the reservoir just by swimming only through oil. But once you start injecting water during the secondary recovery, at the displaced zone, see like what is happening, at the end of the water flooding, some of that oil is getting discontinued, and trapped in that pores. Once, the size of the trapped oil blob is actually larger than the space between these two grains. And hence, that cannot go from here to the other side. So once that happens, if you are injecting water, water can just bypass and produce on its own without bringing any oil out. This is capillary trapping, of oil. And it is because of the high interfacial tension between the oil and water. The oil droplet is like a stiff balloon. If we attempt a big balloon to actually push it through a small, keyhole or something, it would not come to the other side, right? The stiffness is what is actually blocking. So we need to attack that stiffness to produce some more of the trapped oil. That is a pore scale mechanism. We also have reservoir scale mechanisms. Of course, these pores are like micron size, micro pores, or maybe even in extreme cases, nano pores. But reservoir scales are like miles or kilometers scale. And for example, between the injection well and the production well, if there is a high permeability zone, we call it as a thief zone, the injected or the displacing fluid would actually bypass through that zone, and it would not actually go to the other zones. Even in the swept zone, that high permeability zone, we know that we have that capillary trapping, right? In the other zones, it didn't even go. So that is one of the reservoir scale mechanisms why there is so much oil left after the secondary recovery. And another reason is a gravity override. For example, if you are injecting a lighter fluid like a natural gas or something to recover this heavier oil, because of its density, the gas actually tends to flow at the top of the reservoir. It would not come to the bottom, and hence that bottom part is unswept. Likewise, if you inject water, it would actually tend to flow at the bottom and leaving the top portion unswept. Either way, it is gravity override, density aspect. And then we have viscous fingering. What does it mean is, if the displacing fluid is has less viscosity or less viscous than the oil, so it would, instead of like a piston sweep, clean flow sweep, it would actually form finger-like structures, leaving the between the fingers unswept zones. So again, these are all reservoir scale mechanisms. These are the reasons why so much oil, maybe 85%. 85% is like conventional reservoirs. When it comes to these recent shales and all those things, probably you may not have any primary recovery at all. Secondary, maybe 5%. Most of it is probably EOR, or maybe hydraulic fracturing, all those things. That's even a worst case thing. Okay, so we have two dimensionless numbers here, capillary number and mobility ratio. So these dimensionless numbers help us what we should do in order to get more oil out of the reservoir after the secondary recovery. For example, here capillary number is defined as V mu, which is these two parameters are for the displacing fluid, velocity of the displacing fluid and the viscosity of the displacing fluid. These two parameters together represent viscous forces. And over sigma, which is the interfacial tension between the oil and water, that's what it is making it stiff, the droplet. And the theta is the contact angle, wettability. These two parameters at the denominator are representing interfacial forces. So it is a ratio of viscous to interfacial forces. So if the interfacial force dominate, that pore scale trapping is exists actually, because water try to drag the oil droplet along with it due to viscous forces. But if the capillary force dominates the viscous force, it would not move. So, and hence what we need to do, we should increase this capillary number by manipulating one or more of these parameters so that you can expect some more oil. Obviously, the velocity of the injecting fluid, we cannot really control it because we cannot power wash a reservoir. If you have an oil mark or something, power washing would work actually. In the reservoir, the velocity is determined by reservoir itself, basically. So we don't really attempt, that parameter, but the other three, viscosity of the displacing fluid. If you increase the viscosity of the displacing fluid, viscous fingering will be addressed, right? It would not actually form fingers. Higher the viscosity of the oil, water, or the displacing fluid, that's a positive thing. Or you can reduce the interfacial tension so that stiffness would go down, and it can easily change its shape, the fluid, and then come from one pore to the other pore and so on to the production valve. So likewise, theta wettability, you can manipulate the wettability using surfactants so that the capillary number increases and you can expect some more oil out. Likewise, mobility ratio, I'll quickly talk about it also. These are the effective permeabilities of the displacing and displaced phases, the case. And the mu is again the viscosity of the displacing and displaced phases. So we need to reduce the mobility ratio. Here by either increasing the viscosity of the displacing fluid or decreasing the viscosity of the oil. So how we are going to be able to do how we are able to decrease the viscosity of oil? Maybe by injecting steam. If you heat it up, it lightens, right? How can we actually increase the viscosity of water? Maybe adding a polymer. So those are all actually these EOR techniques. Once you know what is happening with respect to physics, of course, you would develop a technology to basically attack those that physics, right? So, for example, there are various types of EOR techniques. chemical flooding where we can inject alkaline, surfactant, and polymer mixer, for enhanced oil recovery. What they do is alkaline and surfactant favorably attacks it reduces the surface tension, interfacial tension, and favorably changes the contact angle, theta. And polymer actually increases the viscosity of the, displacing fluid. Three effects at the same time. You can expect some, more oil recovery. Likewise, low salinity water flooding, I'm going to talk about it later in detail. And thermal flooding, basically to reduce the viscosity of the oil, which is good. Immiscible flooding and miscible flooding, basically you inject a gas and it dissolves in the oil and lightens it, reduces the viscosity and reduces the interfacial tension. There are some positive effects to favorably change the mobility ratio and the capillary number. So recently, nanofluids and ionic liquids are also used for especially wettability alteration and to some degree interfacial tension reduction also. So this is one of our work, like using nanofluids for enhanced oil recovery. So what you are seeing here is, by the way, the scale bar, the black line is 100 micron, meaning that from one side of this picture to the other side, maybe a millimeter. So what you are seeing here is, it is a microfluidic chip. It's not a chip per se, it's a small portion of the chip. The chip is 2 centimeter by 1 centimeter, but what we are seeing is like a 1 millimeter across. So this is a dead end pore. This is a pore, and dead end, it only has entrance. It does not have the exit. So we injected oil, we saturated the chip with oil first, and then followed by, the objective is like, we inject the water from the same well, we call it as produced water, to see if this difficult to produce water can be produced. So we did water flooding and the water was not able to even go in, because of course it does not have the exit. Even when we have the exits, you see that at corners, outside the pore, oil is stuck. Water can go there, but it is not able to recover even outside. Inside, it didn't really work. So then that water, when we replace that water with our proprietary nanofluid, see like what happens. So the wettability alteration, you see like this was oil wet, now it is becoming water wet, and oil is getting out. You see that internal inside also, it's actually separating, nanofluid is separating the oil from the rock, changing the wettability. So of course, I mean, that's like it happened in a day, like in a small, thing. Sometimes it is like probably happens in 15 minutes, day, or sometimes it may not even happen depending upon rock, oil, and water properties. Okay, so then this is latest technology, but coming back to our objective, is like using produced water, especially high salinity produced water, for enhanced oil recovery purpose. Unfortunately, high salinity produced water is not useful for enhanced oil recovery. As you could see here, this is again another microfluidics based experiment. What you are seeing is like a microfluidic channel of I think around 500 micron across, and you're not seeing the entire channel, part of it. And this is the flow direction. So it's a microfluidic channel made of glass, but we transformed it to carbonates by some in-house, geomaterial microfluidic technique. And then that has a carbonate surface now. And we injected high salinity water through that channel first. We let it soak, and then followed by a model oil. We call it as like acid number 1.5 oil, and to displace the water. In a straight channel, any fluid can displace any other fluid. So it did displace. Water was displaced. Maybe there may be a film of water, but mostly oil, and not in this situation, like it was all oil, and then we let it soak. What happened is some of the surfactant molecules, natural surfactant molecules in the oil actually made that initially water wet reservoir into oil wet reservoir, overnight. And then, when we tried to inject the same high salinity brine again to displace the oil, a big blob of oil is stuck to the surface. Ideally it should not stuck, but you see that a big blob from one side to the other side, when we were flowing that fluid, it was not even responding. I'll play that video. But when that high salinity fluid is replaced by a lower salinity fluid, you will see like what happens. So direction of the flow and time, and the high salinity fluid is flowing and stopped and then replaced by a lower salinity fluid. It's getting released. You can see, its wettability is altering, yeah, once it loses its contact, then it would actually flow. So meaning that lower salinity fluid might actually do better than the high salinity fluid. But if we want to reuse the high salinity fluid for this purpose, what we should do? We should dilute it with, maybe potable water or something like that, which we don't want to do. So instead, the idea is, okay, can we use that high salinity fluid by itself? By itself in the sense, what will happen if we actually carbonate that high salinity water by adding CO2 into it and inject that carbonated water into the reservoir with the expectation that some enhanced oil recovery along with some of that water or maybe all of that water will be disposed of, right? Along with, some CO2 sequestration. So one shot, three birds, basically. So very ambitious objective. We are testing it now. And that objective requires us to know, how much CO2, like what would be the solubility of CO2 in oils and waters. Because, the properties for sequestration purpose to quantify how much CO2 is permanently sequestered in the oil and water phases, yeah, and as a free phase, right? For all those quantifications, we need to know the solubilities. So, and of course, I didn't talk about the produced water in depth, but as Dr. Wagner mentioned, we have like more than 1 million actively producing oil and gas wells in the states itself, and then on average about almost like 9.2 barrels of water produced with each barrel of oil. We should actually technically call those wells as water wells than oil wells, but we still call it as oil well. So again, 97 barrels of water produces along with 1 MMSCF of gas also, natural gas. So a lot of water. And to put it in the perspective, and in 2021, USA generated approximately 26 billion barrels of, or trillion barrels probably, maybe could be trillion, yeah, barrels of produced water, with huge quantities, and that which is actually 70 times more in volume compared to all other liquid hazardous waste. The single most dominating liquid hazardous waste is produced water. And that's the reason why we have a separate wing to tackle it. And I think we all probably, some of you might have felt the earthquake a couple of weeks ago, right? A week. That is because of produced water. I cannot conclusively say, but we know that produced water reinjection into class 2 wells is one of the reasons for, or maybe the reason for induced seismicity, which we don't want. Instead of injecting that into class 2 injection wells, if you use that water for enhanced oil recovery, the difference between class 2 injection wells and using it for enhanced oil recovery is Class 2 injection wells is like you are injecting into a dead end. The pressure is rising and all the seismicity is getting affected. But in the oil, for oil recovery, you're injecting this fluid and producing another fluid. So basically, you can manage the pressure there, right? And then, yeah, as I already mentioned, to tackle all these global warming things, CO2 sequestration and produce water disposal and enhance oil recovery, we proposed high salinity carbonated produced water flooding. And hence, we need to know the solubilities of CO2 in aqueous and organic fluids. And this work is how to measure them in the lab and model them using maybe any existing methods. So we attempted to actually measure the CO2 solubility in aqueous brines and also produce water samples and hydrocarbons, regular hydrocarbons and a crude oil as well. I'm going to show you the results. And then we also attempted to actually use a state-of-the-art thermodynamic model to predict the solubility of CO2 in brines and compared it with our experimental results. So this is an experimental setup or the procedure we use to measure the solubility of water, solubility of CO2 in brines. It's a very simple process, from the first principles. What we were doing was we were actually saturating water or the brine with the CO2 in this pressure cell, and then taking a small sample of that carbonated water through this back pressure regulator into this, oil, which is at atmospheric pressure. Once you actually take that soda and put it into this atmospheric cell, the water and the gas has to separate because, and then we measure the weight of the water or the aqueous fluid and the volume of the gas. And that's enough to, know the saturation or the solubility of CO2 in the, it's a simple process, but when to do it, it requires, a lot of skill. And also the back pressure regulator that you're seeing here is the world's most sensitive back pressure regulator. It requires high-end, instrumentation basically. And then the same technique would not be useful to measure the solubility of CO2 in the oils, unfortunately. Because, some of the components of the oil, lighter components can actually diffuse into the carbon dioxide. And then, you cannot do this weight versus weight volume approach. And hence we had to actually build a different system. The working principle here is basically we have a high pressure glass capillary. We take a certain known volume of oil into that capillary tube and then pressurize that with oil, CO2. What happens is, unlike when we pressurize, brine with CO2, in this case, oils swell significantly. Water doesn't swell, and the swelling, the swollen volume is a representation of the solubility, how much CO2, is dissolved. So what all we need is the initial volume and the final volume, stabilizer volume. From those, we can calculate the swelling factor, and from swelling factor to the solubility. So, and then this is the model that we used. And of course, we used some machine learning also along with this model. And it is a very potent model and covers a very high range of temperatures, pressures, and salinities. Practically, it covers the entire range we require, or more than that. So here are the results. This is a plot between the pressure, versus the CO2 solubility. What you are seeing here is the solid lines are the experimental data, and these what are those? Dotted lines are the model. Okay, so this is deionized water, and next salinity, and the highest salinity is here. The trend is basically as the salinity increases, at every pressure, the solubility of CO2 in that brine decreases. And as the pressure increases in all the fluids, solubility increases, as you could see here, until 1000 psi, and above that, the increment is like insignificant. And that's one trend. And the model and the experimental measurements are like decently matched. And then the same data here, this plot also pretty much, except we also have experimental data for 2 produced water samples in this plot. We do not know the composition of the produced water. We know the TDS and we know the density of the produced water. And so this produced water sample density is actually between the DI water and 1 molar NaCl brine. And the solubility perfectly fell in between, and hence we thought, okay, there may be a strong, some kind of relationship between the density of the water and how much CO2 it can dissolve. And then we plotted our data that way, and we saw strong relationships, density of the brine versus CO2 solubility at different pressures. Each line represents a pressure. For all the fluids tested, see the correlation coefficients exponentially, decreasing the solubility with density. Correlation coefficients are 99% plus for all of them. So this is one of our findings. What does it mean is, if you know the density of your produced water, probably you should be able to, estimate the solubility of CO2 in it just from the density. So, I mean, without knowing the composition and all those things, which is a good thing. Then coming to the oil solubility work, as I said, we used 3 different hydrocarbons of different molecular weights, hexane to dodecane, and a crude oil. For all of them, these blue lines, as the pressure increases, the solubility is increasing for all of them. That's a trend. And then as the molecular weight is increasing, the solubility is decreasing. Hexane dissolved more CO2 than dodecane. And we do not know the molecular weight of our crude oil, but we would guess, the crude oil has even more heavier components and its molecular weight would be even heavier than the dodecane, and it has a lower, solubility. And the green lines are actually the swelling factor, lines. At low pressures, the swelling factors are not that high, but especially for decane at 700 psi, swelling factor was more than 7. What does it mean is 1 ml of decane saturated with CO2 at that pressure swollen 7 times. Which is a very good thing for enhanced oil recovery. If it swells, viscosity reduces. If it swells high enough, the 2 droplets next to each other, isolated, might even combine again back and flow, right? Good thing. So you could see here decane, like initial volume and the final volume, around 30, around 80. So that corresponds to this data point. And each brine experiment was actually repeated 3 times. Each time we got 5 data points. Basically, all those points are brine data. Each data point is 15 replicates. Here, each data point is 3 replicates. And so then the conclusion is swelling factor increases with pressure, as you could see here, but higher at higher pressures. And solubility decreases with increase in molecular weight of hydrocarbons. And we also tried the same way, if there is any trend between the density of hydrocarbon versus the CO2 solubility. Previously, it was exponential decline, right? Now it is a decline again, but it is linear decline. So for all pressures, again, pretty decent correlation coefficients, more than 90% for all of them. So again, this is a new finding. And so these data points are for hexane, and these are decane, and this is dodecane and the crude oil data points. All of them are falling on that line. So meaning that if you know the density of the crude oil, you should be able to, predict the CO2 solubility. Again, we did another experiment where what happens if you also have water along with oil, what happens to the swelling factor of the oil? Would the presence of water has any influence on the swelling factor of the oil? We made some modifications to the system so that, we can have both oil and water in the column, and then water doesn't swell. It takes CO2 in, but it doesn't swell, but oil swells. Measurement point of view is the same thing like before. And then when we compare the experiments with in the presence and absence of water, what we found is at lower pressures, for all the, three systems we tested, there is no, by the way, blues are like in the presence of water, and this orange is like in the absence of water, for three different, hydrocarbons. Up to this, all these data points, there is no significant difference. There is no effect of, presence of water. But at higher pressures, 700 psi, see, like, this is like with water, this is without. This is with water, without water, with and without. So for even hexane, lower molecular weight, we have seen some difference here also. So the conclusion is that when we have like water along with the oil in it, the swelling factors are and probably solubilities are smaller compared to when we don't have water. So here are some quick conclusions. Just a recap. CO2 solubility in the tested brines and hydrocarbons increases with pressure. I mean, it's intuitive. With pressure, solubility should increase. But the good thing is that we have a tool to measure the solubilities, for unknown systems like, produced waters with a lot of, chemistry in it. So above 1000 psi, CO2 solubility in the tested brines did not change much. As brine density increases, CO2 solubility decreased exponentially, basically. And CO2 solubility in brine matches well with the model predictions, meaning that we can use that model, to predict the CO2 solubility without conducting the experiments. The issue is that it may not work for produced waters because it has so many salts. The model considered only sodium chloride. So if you have multiple salts and all those things, and hence our experimental system, should be used. CO2 solubility decreases with increase in molecular weight of hydrocarbons. Meaning that if you have a heavier oil, CO2 dissolution may not be that much in it, and hence it would not swell that much. So probably CO2, sequestration, I mean, like EOR is better for lighter oils, which is also a kind of known information, except we proved it experimentally. As hydrocarbon density increases, CO2 solubility decreases linearly. So this was exponentially for brine, and here linearly. Trends were different. At high pressure, presence of water reduced oil swelling factor. And here is our team, and myself and Dr. HL is my collaborator, and Dr. Sushovan Pradhan is my postdoc. He also did PhD with me. He was the one who did all these experiments. And I mean, as I said, they are high pressure experiments. He's dealing with very little volumes, all those things. Like it was like a couple of years work, because we were waiting for each data point, like for oil swelling experiments, 3 days, 4 days, because it was all due to diffusion only. We are not stirring or doing anything. So, and then the modeling work was done by my PhD student, Mr. Rupam Bhattacharjee. And so, of course, without the funding sources of this work would not have been possible. And the major funding source for this work is like NSFF score grant that that is continuous now. And we also got some funds from Hamilton Syringe Company. By the way, if anybody wants to use it, like they monthly fund actually $1,000, $2,000 kind of grants. It's very easy, actually, simple grant. I mean, you would immediately know. You submit it, and then whether they accept it or reject it, you can use those funds to buy high pressure syringes or anything, or even any other things also outside. So that was it. And if you have any questions, I will be glad to answer. Sorry, I mean, it was like super fast train. So.
Well, thanks for your seminar. I'm always curious about next steps. What is the next steps? Maybe the cases number one, next steps with your research, where you go with that. But kind of more broadly, when do you see this being ready for prime time, ready for application within the industry?
Yeah. I mean, this project also involves, some microfluidic testing, basically prepare these brines, inject it into microfluidic chips. What happens? Some of that oil will be displaced. Some of the remaining oil would swell, right? And there will be some CO2 dissolved in the water. So if you look at, for example, this picture, this one. So now the volume of oil is the real volume of the oil here, because there is no swelling involved, right? So by just seeing it, like what is the volume of it. By the way, the depth of that thing is like 20 micron, which I did not mention. So, but if you inject CO2 or carbonated water, the oil swells. How do you know, what is the remaining oil volume? That, volume that you're seeing is not the real volume, right? So the swollen volume, and you can back calculate what should be its original volume and how much CO2 is dissolved in it. Likewise, how much CO2 is dissolved in the water, right? And that way, how much produced water is disposed, how much sequestration happened, and what is the true enhanced oil recovery. So the reason why we are actually measuring all these things is basically for this application. Once we use those fluids for enhanced oil recovery, it's not like just using regular water where swelling and all those things would not occur. To quantify these sequestration, produced water disposal, and enhanced oil recovery efficiencies, we did this work, and also we have actually started working on the next step also. We are actually conducting microfluidics experiments using high salinity carbonated water. And so we are on the way. And of course, the ultimate thing is like using this in the field. So, yeah.
So first of all, thank you so much for the talk, because I don't have any background in petroleum engineering, so I really understand now the complexities of what is involved in this.
It's actually more complex.
I'm sure, but at least I have a sense of.
Thank you. Yeah.
So I have two questions. One is more big picture, and it's more related to the carbon sequestration, and I don't know this, so I'm asking you. So you're introducing all the carbon dioxide. How does it change the alkalinity and hardness of the water, because you're adding so much carbon dioxide, right?
That's an issue. Yeah. You can probably expect some precipitations actually, because salts actually might actually precipitate. It's a very, very complex process, and it involves, somebody should actually consider, the chemistry of the fluids and rock fluid interactions, all those things. And then if any precipitation is happening, especially near wellbore, that might actually block, blockage for further injection. So there should be a mitigation process, or maybe there should be countermeasures basically not to happen, that all those things, obviously. Yeah.
A second question is more related to the solubility of carbon dioxide in that brine. So in the model that you showed, it's nice that your model had very good agreement with your experiments, especially for the brines. I was just curious why it did not match for DI.
DI water is also a pretty good match.
Yeah, but it's consistent. For me, that's opposite, because usually for DI you have very good matches, and then for real waters you get you don't.
Great, Charanmaya. Thank you so much for this observing and asking. And I cannot conclusively say the reason, but what my intuition is saying is that that experiment, the original model was built like using some experimental data. Okay. And so all the brine data, you see that all the brine data is latest data. Okay. Obviously, the DI water data is 1940s, 1930s, experimental uncertainties and all those things may be there. If you look at the data of our data, for example, if the dotted lines are our data, and if that is the model prediction, and then we can say maybe we did not saturate it fully, right? Consistently, our data is, we have higher solubility than the model, meaning that probably, the experimental data, the model is not doing well.
So that model is based, it's an empirical model. It's not based off of first principle.
To some extent, it is a thermodynamic model, but there are some parameters that requires tuning
Sure.
by the experimental data. So if the experimental data, original data has issues, yeah.
Thank you.
Great questions.
Right, thank you again for being here.
It looks like
Oh, you
yes,
got one
question.
more? Oh,
Yeah, please. Yeah.
Yeah,
We have time. Yeah.
I'll probably go on a tangent and think about more broader aspect of things. So we are talking about carbon sequestration. So we are trying to plant carbon in the soil or sediments, right? So, but how I approach this is that we have a higher carbon dioxide concentration in the atmosphere now. And then for that, due to that, we have higher temperature. So I see the positive end of these things, which is, we can plant our crops early. We can have a longer growing season, and carbon dioxide is plant food based.
Sure, of course.
So I can see the other way as
Yeah.
well. Maybe the carbon dioxide isn't so bad, but definitely we need to control the rate at which it is increasing.
Sure.
So we all
Definitely.
That's
That's the reason why, soil sequestration exists in the first place, right?
Yeah.
But of course, as you would probably agree, it's not really the permanent solution, right? So whereas, a rightly executed, CO2 sequestration, like this, in the porous media probably is more permanent. It's again, so it's coming into the atmosphere again, right? Soil thing, like it's a cyclical thing, so. Yeah. But all these things should, first of all, there is still debate whether this global warming thing is a reality or not. Like they say, some say like it is a cause, some say it is an effect, we don't know, but it's a science. If global, what is that? Global, the CO2 is greenhouse gas. The greenhouse thing is, science. We know it actually when you have CO2, in a chamber or something like that, the temperature rises. Anybody can test that. So, but if that is what is causing this global warming effect globally or not, we don't know, but I believe it. And all these things should actually come together. Soil sequestration and all those things basically tackle that problem. In 2021, and now it is 24, right? In the last 3 years, I think it only increased a few ppm, like 2 ppm, 3 ppm. Because I used my old presentation, updated it actually. So when I looked at it, actually it was 419, now it is 421. So maybe it slowed down actually. So yeah, I don't know. We can always check the data. It is updated daily. Even yesterday's data we can actually see.
Thank you.
Thank you so much for attending.
Questions in the chat? All right, let's thank Dr. Bikkina again. Appreciate you being here.
Thank you.
Just real quick, we're gonna take a break in March, in observance of spring break, so we won't have a seminar then. But then we'll be back April 18th with Dr. Kieran Minglegiri from Biosystems and Ag Engineering, and then May 16th will be our last of the semester. We'll have Dr. Sherry Hunt from the USDA Ag Research Service. So hope to see you then. Thanks again for being here.